Look deep into nature, and then you will understand everything better. That's often linked to Einstein, and it feels very relevant for our deep dive today. Welcome back, everyone.
Welcome. Our mission, as always, is to sift through some important sources and pull out the key knowledge for you.
Because, yeah, understanding nature, especially something as complex as the Earth's climate, it means you're always learning, right? Always refining things based on new evidence.
Exactly. And that's just what's happened with a really critical part of the climate system, the Atlantic Meridional Overturning Circulation.
You'll hear it called the AMOC. Sounds a bit technical, maybe?
A little, perhaps, but it's essentially a huge system of ocean currents. Think of it like a giant engine driving weather patterns.
And we're looking today at a new study. It's just been published in Nature Geoscience, and we're working from a release by Caltech.
And the interesting thing is it paints a significantly different picture of the AMOC's future compared to a lot of the earlier projections.
Yeah. Right. So that's our focus for this deep dive, unpacking what this new research found. What does it mean for how we understand this current? Why does it matter? And how does it maybe challenge what we thought we knew?
And, this kind of understanding is vital for staying informed about climate change, definitely.
And also the kind of interconnected, detailed knowledge that, well, it can be really useful for things like the UPSC mains or prelims exams, or just for anyone wanting a deeper grasp of global systems.
So let's get into it. The AMOC. You called it an engine. What exactly is it doing?
So at its core, it's this massive network of currents moving water around the Atlantic, vertically, horizontally.
Yeah.
And its main job, according to the source, is basically shipping heat from the southern hemisphere up to the northern hemisphere.
And that movement is all driven by differences in the water's density, right? Like temperature and how salty it is.
Exactly. Think of it like warm, salty water flowing north near the top.
Okay.
Then it gets up north, cools down, gets denser, and sinks.
The overturning part.
That's it. And then that cold, deep water flows back south. This whole cycle is what moves the heat around and helps regulate climate.
And that heat regulation has a huge impact on weather, doesn't it?
Oh, absolutely. The source mentions it helps keep Western Europe relatively mild for its latitude.
And it influences monsoon seasons, too, like in West Africa and India.
Yeah, it's linked to those as well. It really is a critical piece of the Earth's climate machinery.
Okay. Now, for a while, climate models looking ahead under global warming scenarios, they were suggesting some pretty worrying things about the AMOC.
They were. The long-standing prediction for many of these models was that the circulation would weaken, quite significantly, in fact.
Some even projected what they called a near collapse compared to how it is now.
And if that happened, the predicted consequences sounded, well, quite severe.
Yes. The source lists things like big changes in regional sea level rise, major shifts in climate patterns.
Here are specific examples.
Things like potentially much colder weather across northern Europe, or drier conditions in places like parts of the Amazon or West Africa.
So these potential impacts really explain why everyone was so focused on studying how much the AMOC might weaken. It wasn't just an academic question.
Not at all. It pointed to a potential major disruption. And we know from looking back in time from paleoclimate records that the AMOC can change dramatically.
Like during the last ice age.
Exactly. Around 20,000 years ago, there's evidence the AMOC weakened. And that coincided with really big, rapid climate shifts, especially around the North Atlantic. So that history kind of fed the concern.
But now, this new study comes along, and it's suggesting something different, a less drastic future.
That seems to be the main finding, yes. It suggests the AMOC will likely still weaken because of climate change.
Okay.
But probably to a much lesser extent than many of those earlier projections were indicating.
Right. So what are they actually projecting? What kind of number are we talking about?
The study estimates a weakening by the end of this century of somewhere around 18 to 43%.
18 to 43%. That's definitely weakening, but it doesn't sound like a near collapse, does it?
No, it's a very different scale of change. The lead author, David Bonin, puts it clearly. He says their results imply more of a limited decline, not a substantial one. Still weakening, yes, but less drastic.
That's a really important shift in perspective. How did they arrive at that conclusion? What did they do differently?
Well, they didn't rely solely on the really complex global climate models, the big ones. They developed a somewhat simpler physical model.
Simpler how?
Based more directly on fundamental principles, like how water density differences drive things, the depth of the circulation, that sort of thing.
Okay.
But the really crucial difference, it seems, was that they incorporated real-world measurements of the AMOC, actual observations.
Ah, so they weren't just simulating it in isolation. They tied it to what's actually happening out there.
Precisely. They used about 20 years worth of data from monitoring arrays in the Atlantic and other observations to kind of constrain their model.
So grounding the physics in reality.
That seems to be the key. Using those real-world observations appears to be a major factor in getting this different, perhaps more refined projection.
Okay, this leads to a really interesting question then. If this new study, using basic physics plus real data, points to less weakening, why did so many other models predict something much more severe? And why was there such a spread in their predictions?
Yeah, that's where this study offers some really valuable insight, actually, into the models themselves. They looked into why there was such a wide range in the 21st century projections from different models.
And they found a link.
They did. They found a connection between how strong a model simulated the AMOC today, in the present day, and how much weakening that same model predicted for the future under climate change.
Okay, wait, let me get this straight. Models that showed a stronger current now predicted more weakening later. That feels backwards somehow.
It does seem a bit counterintuitive at first glance, doesn't it? You'd think stronger means more robust.
Right. So why would a stronger present-day simulation lead to predicting more future weakening?
Okay, this is the core of their explanation. It boils down to the simulated depth of the AMOC in those models. Remember we talked about the cold water sinking and flowing south deep down?
Yeah, the deep return flow.
Right. So in many of the models that simulated a stronger present-day AMOC, that deep return flow reached much deeper into the ocean.
Okay.
Now think about climate change impacts. Warming surface waters, more fresh water from melting ice. These things happen at the surface and make the water less dense, less likely to sink.
Makes sense.
In the models where the AMOC was simulated as being very, very deep, those surface changes could actually penetrate further down and have a bigger impact on the deeper parts of the circulation.
Ah, so a deeper simulated current was actually more vulnerable to the surface changes that cause weakening.
That's exactly what they found. The depth allowed those surface effects to drive a greater overall weakening throughout the model system.
So models starting with a deeper, stronger AMOC were, in a way, less resilient in the simulation compared to models that simulated a shallower current.
Precisely. Those models with a shallower simulated AMOC still showed weakening, but the scale wasn't as dramatic because the surface changes didn't disrupt the deep flow quite as much.
Wow. And this brings us right back to the importance of those real-world observations.
Absolutely critical, because the study used those observations to figure out what the real AMOC looks like today, and the key finding there. The actual real-world AMOC is relatively shallow compared to how it was simulated in most of those climate models predicting the really drastic weakening.
There it is, the connection. The models predicting a near collapse were often working from a starting point, a simulated present-day AMOC, that was deeper than the real thing actually is.
That's the strong implication, yes. Since the real AOC is shallower, its response to climate change seems likely to align more closely with those models that also had a shallower circulation.
Which predicts less weakening.
Exactly. Even under high emissions scenarios, this new study suggests only that limited weakening, largely because the real system isn't as deep as some models assumed.
So it sounds like a lot of the previous uncertainty and those more extreme projections might have stemmed less from misunderstanding the physics of weakening and more from biases in how the models simulated the ocean's starting conditions.
Specifically, biases in simulating the ocean's density structure, how those layers of water with different densities are arranged. If a model gets that density stratification wrong, it might simulate an AMOC that's unrealistically deep.
Which then leads to an overestimate of future weakening when you apply climate change forcing.
It seems that way. It really highlights just how vital basic research is, and especially getting those real-world observations integrated into the models.
You really can't overstate the importance of that observational data.
No, you can't. David Bonin is quoted again saying, "There is immense value in doing basic research. It can give us a better indication of what the future might look like. And this study is a perfect example of that."
And it's not the end of the story, of course. Science keeps evolving.
Absolutely. The researchers themselves point out the need to look closely at newer, higher resolution climate models, models that have more sophisticated ways of representing ocean processes.
To see if they capture these dynamics even better.
Right. This study kind of provides a framework, a benchmark, using real-world data to help evaluate those more complex models going forward.
It's that constant interplay between theory, modeling, and observation.
Yeah.
And it takes a team effort.
Definitely. The paper credits authors from places like University of Washington, Caltech, and it's supported by groups like the National Science Foundation, the Packard Foundation, Schmidt Sciences. It's collaborative work.
So let's circle back to you, our listener. Why does digging into this detail matter for you?
Well, first, it gives you a more refined understanding of a really key part of the global climate system. That's important context for understanding broader climate news and discussions.
And it also shows you how science progresses, doesn't it? New data comes in, models get tested and refined, and our picture of the future gets updated.
Exactly. Sometimes, like here, that update might suggest a particular risk, like AMOC collapse, is maybe less imminent or severe than previously feared based on some models, but it always adds nuance.
It also really underlines how incredibly complex climate modeling is, and why grounding those models with real-world data is just non-negotiable. It's essential.
So whether you're just trying to stay informed or perhaps preparing for exams like UPSC, where understanding these large-scale systems is crucial.
Or even if you're just curious about how our planet works, grasping these concepts, what the AOC does, how modeling works, the power of observation, it's really valuable knowledge. Okay, so wrapping up the main takeaway from this deep dive. New research, crucially backed by real ocean measurements, suggests the AMOC is likely to weaken less drastically this century than some earlier projections indicated.
And a big reason for that difference seems to be that the real AMOC is shallower than it was often simulated in those models that predicted more extreme weakening. Getting the present right helps predict the future better.
A really important refinement. Now, here's something to maybe chew on after we finish. While this specific study might offer a less alarming outlook for the AMOC itself, what does this whole process of needing new data to significantly revise projections from complex models tell us about the inherent challenge, the uncertainties involved in trying to predict the future of Earth's climate system as a whole? It's just so vast and interconnected.
That's a great point. It's a reminder that scientific understanding is always evolving, always being tested against reality. It's a journey.
Definitely something to think about how we approach scientific predictions and understand the process behind them.
If you found this deep dive useful, and you want more insights like this into complex topics, we'd really appreciate it if you'd like and subscribe.
And please do leave a comment below. Any questions you still have or your own thoughts on this AMOC update, we'd love to hear them.
Just to reiterate, our discussion today was based on that new study in Nature Geoscience, adapted from a release by the California Institute of Technology.
Thank you for joining us for the deep dive.